Yeah, let's just start for this morning session. So yesterday we have learned about the properties, the measurement characteristics. We have learned about um, some basic theories, related to the measurement process. Basic theories related to the measurement process itself, and some statistical basic knowledges which we have reviewed also yesterday, so that we know what to measure, how to measure it, and yeah. So in this session, in this today's session, we are going to continue further on the basic sensor characteristics that we need to understand. Also, how to assess uh, whether one sensor is better than another. Yesterday, we have learned that calibration is an important part of any measurement. Before we can use the sensor or instrumentation or any measurement system in a real measurement to measure to measure unknown parameter from unknown measurement, we have to calibrate it first. We have to calibrate the sensor, or we have to calibrate the measurement system or the instrumentation first against a standard. What is a standard? A standard is measuring an object which has known value of that particular measurement. Not only a single, but usually multiples with different values, and then we can do calibration. Yeah, by comparing, by drawing the calibration line, and then getting getting the calibration equation of that particular sensor. So the minimum which we need to have is that what we call as a 3-point calibration. 3-point calibration. So at least we have to have 3 points. Why to have 3 points? So that then we can draw the line nicely. 1, 2, 3, for example. Like this. Of course, each of this will be usually also measured multiple times. And this is what we call as calibration line. This is the input of which is the measurement that we want to know, and then the y is then the reading of the scale of our sensor. Okay, so the 3-point calibration can be done by using zero measurement, this one is the background measurement. When you don't put anything to the sensor or to the instrumentation, then you put another two calibration object, two calibration object here at x1, at x2, where then you will capture its response at x1 and x2. From there, you can draw the calibration line. Then what you are doing actually when you are measuring is you compare the unknown measurement of unknown parameter with this calibration line. So for example, then if you have a reading here, let's say y unknown, yu, what you are doing when you are measuring, basically you put this yu into the calibration line to obtain the xu. This is what in the process of the measurement itself. So the red part here was the calibration here. and the purple part is the measurement. After which, how do we know whether that measurement is accurate or not? That is the step what we call as validation. So against the same object, unknown object, which whose value we want to know, we want to measure, then we put that object in another more standard measurement method, to validate it. Let's say, for example, COVID-19 detection, SARS-CoV-2 diagnostic. You are developing a new type of sensor. Let's say, for example, a new type of biosensor using electrochemistry and antibody. And you have this, and then you have to put the same sample from the patient into PCR to see whether the sample really contains SARS-CoV-2 virus or not. But in this case, it will be just qualitative data, yes or no, existing or non-existing of the virus. Let's say another example. Give another example: glucose level. We are developing also a new biosensor to detect the quantity of the glucose inside the blood. Then, after you do this, you do the calibration to your sensor. You do measurement here in the purple to obtain XU. To know the accuracy, whether this is correct or not, you have to validate. You put the same blood sample into, for example, existing blood analyzer, where you will put where it has its own calibration chart. So it has its own calibration chart. Let's say, let's draw it here for example, this another example. Okay, so for example, in this graph, let's say this is another graph, that the value of the reading, this is for validation, another calibration chart, that the reading is in this value. Let's say this will be ZU, so its reading will be then here, okay, here. So you obtain then this is XU, let's say this is ZU. So then you will obtain Zn minus Xn here as the accuracy of your new sensor. Okay, the error, the difference between the two is the error. Here we consider Zn or Zu here as the more accurate result of the measurement, because it is done using a more standardized sensor or standardized instrumentation. So it is more acceptable, the value of which is more acceptable. The previous one, the purple one, XU, is from your new sensor. So the error between two shows the error from your measurement, from your sensor. The accuracy will be 1 minus that error times 100% divided by the accurate value, Zn, and times 100%. Okay, I hope it's clear enough. So this is the way how to characterize your sensor. First is you have to do calibration, the red one here, where you compare the output of the reading of your sensor or your instrumentation with a known standard. A known standard means an object which you know. For example, in the case of blood glucose meter, then you would have, for example, a blood sample which you already measure how much the glucose level is inside that blood. Okay. After which you calibrate. Then you measure the purple one, you measure an unknown sample from a new person completely. You obtain here YU, then put into the calibration line, you will obtain the measurement result XN. But in order to get the accuracy, you have to validate that result, using a more standardized, more standard measurement method. Let's say, for example, using HPLC or using high performance liquid chromatography or using UV visual spectrophotometer, etc. to get this green and then comparing the result between the two. So if you read journal papers that deals with the development of new sensors, so all these factors have to be usually put there. The calibration has to be there, then the validation has to be there. Okay. Okay, so let's now get to the other, get to the sensor itself now. Okay. So actually we have discussed this a little bit during introduction to biomedical engineering. So a transducer basically is defined as the device that converts a primary form of energy to an electrical energy for the purpose of measurement or control. Yeah. The primary energy forms here are the primary energy form in the environment, like it could be mechanical, thermal, electromagnetic, optical, or chemical. Sensor, on the other hand, where is a specific type of transducer, where it detects or measures a signal or stimulus. Yeah, here the difference is that a transducer, what we want is we want to acquire information. Remember, so what does it mean? If a sensor, yeah, a sensor is a transducer, a device that converts a primary form of information. So here we change the word in energy into information for sensor, yeah, for sensor, to an electrical form. Let's say electrical form. Yeah, because if you say only transducer, it could also be an energy converting device, like for example a motor. No, like an electric generator. An electric generator converts motions into electrical energy, like what you can see in energy power station. Yeah, pembangkit listrik, yeah. Energy electric generator. it converts electric motion energy, mechanical energy into electrical energy. So what they care here, there is the enthalpy of the energy, the amount of the energy. But in the case of sensor, this is generally in transducer, yeah, any transducer. But for sensor, what we want to know, what we want to convert is the entropy. Yeah, the entropy. It is the state of the energy. The state of the energy basically is the other word for information. So entropy here represents the information. Yeah. So at that time I give examples, for example, between lamp, yeah, the general lamp that you use for lighting in your house, and with your monitor, your computer monitor or the monitor of your smartphone. Okay, in the lamp, what matters is the amount of the electrical energy that is being converted into light energy. Of course, yeah, this is not so. This is more of actuator. In the lamp, you don't really care about how that light is arranged. What you care is that it is bright enough to light the whole room, for example. But in the case of monitor, or either in your smartphone or your computer, you are not, sometimes you don't really want it to be too bright also. You don't want to convert the whole electrical energy into radiation energy, into light. Yeah? If it is too bright, then you will lose information. Right? You will lose the state of the light itself. What you want, what matters in monitor, computer monitor or smartphone monitor is the state of the energy, the darkness variation, the brightness variation of between the pixels in that monitor. And if it is color monitor, then we are also concerned about the red level, green level, blue level of each of the pixel within that monitor. Okay, not just the amount of the energy being converted, but the state of the pixel within the and the arrangement of the pixel within that monitor, such that information is being conveyed, yeah, from the electrical domain into light domain, so that then we can read the a letter in the monitor. In the case of monitor, actually it is not a sensor, but rather it is an actuator. Yeah, it is an actuator. Although in actuator case, yeah, in actuator is a device that converts electrical energy into other primary form of energy. In the case of monitor, it will be into electrical energy into radiation. Although in actuator, usually we use the terminology actuator in more general form for both energy converting element like lamp. You can also use the term actuator, but actually it fits more if it is used for information conversion element or device like monitor. In the case of sensor, usually it is quite specific that it is a device that transform information, from one form of energy or information into another form, especially from the primary form of information, mechanical, electrical, thermal, chemical, etc., into electrical form of information. Yeah, we call it like this. Of course, that currently all of our technology in the world, human-made technology, is based on electronics. So most of the information also is processed in the electrical domain, and that is why that most of these sensors work to convert information from the primary form of energy or primary form of information into electronic domain, electrical domain. Yeah? But some sensor transform this the primary form of information into photonics domain, for example, or magnetic domain. So there is also possibility that we may have cascaded transducer, yeah, cascaded transducer in a one single sensor. For example, like this, and all of these are located within a single sensor. So this is when, for example, the information in the primary form of the energy is not in the form of electronic. Yeah, this is in electronic, for example. Let's say this is in the form of acoustical or mechanical. Sometimes it is the conversion into electronic domain is not straightforward, but rather through several stages within that sensor. It could be from acoustical into another mechanical domain, because acoustical is basically a mechanical domain as well. Another mechanical domain, then for example, to electrical domain, but not yet voltage, but let's say capacity, etc., etc. So we may have several transducer within a single sensor. Okay, so again, the use of the terminology transducer is more general compared to sensor. Sensor, basically, sometimes we use it more specific. Okay. So like this, if the flow of information is from the real world into the intelligent feedback system, usually it is the role of sensor to do the conversion or the processing of that information. But if the information direction is opposite from the intelligent feedback system to the real world, then it is usually the task of the actuator. Okay. So we have learned also in the previous session about errors, and we have learned also some sources of error during the operation of sensor or instrumentation. Insertion error are errors that can occur during the act of the inserting the sensor into the system being measured. Yeah. So when the transducer is too large for the system, then you will basically perturb the system. Yeah? You will disturb the system that you want to measure. So this is then will cause some distortion of information actually from the system whose parameter you want to measure. Or when the transducer itself is too sluggish for dynamic system, too slow. You want to measure, let's say, for example, muscular or let's say brain signal. You put an electrode. However, the amplifier is too the electronic system is too slow. Yeah, then it will cause some error also. Yeah, because it is too slow, it cannot follow the dynamic change of the biosignal. Or you use self-heating transducer. Yeah, that to the extent that the excessive thermal energy from the transducer itself is added to the system, and then it will cause some errors to the measurement. Then there is also error that is caused by the operator. This is considered as application error. For example, we want to measure temperature, but the placement of the sensor itself is put on the wrong part of the body, for example. For example, if you are measuring using infrared, if in the general practitioner, to measure the body temperature, you can now use infrared thermometer. The correct one is actually if you capture from the inside of the body, usually using the infrared gun to the inside of the ear hole, yeah, to get the temperature of the body. Yeah, if it is you use the outer surface, yeah, of the body, usually it can cause error because the outer surface interacts also with the surrounding air and room temperature. Okay. Then we also have characteristics error. These are errors that are inherent in the sensor itself. For example, the DC offset, the incorrect slope, and or not perfectly slope. So what does that mean? DC offset is, for example, if you are measuring, you are doing calibration again. So many of these sensor characteristics are known when we do calibration. You do calibration. Yeah, this is the input of from the standard that you put into the sensor, and this is the reading. When the input to the sensor is 0, so it means the background condition. Ideally, we don't want any output at the sensor, right? And we don't want the sensor to give reading when there is no stimuli or stimulus being put into the sensor. However, in real sensor, usually we still have some value. This value is called as offset. Yeah, for example, if after calibration, so at 0 level, there is the average is here, this here. Then we have this. This is offset. The value of the reading of the sensor when there is no stimuli being given to the sensor. So if it is expressed mathematically, this equation of this linear line would be y equals to mx. The m is the gradient or the slope plus b. B here becomes the offset of that sensor calibration. Incorrect slope means that when we don't have, when the slope, yeah, for example, is not correct, yeah, there is a slope difference or there's a drift, we call it a drift, where the slope changes with time. And that is called as the characteristic error. Not perfectly linear slope. For example, if you do calibration, again, X, for example, you do calibration with more standard sample at background, and for example, at this line, this line, then also another one at the higher values of the input. For example, you obtain this kind of line like this. So this is the average. So when you draw a line across this standard, across this calibration, what you will obtain is something like this. Okay, so it may be linear at the beginning, but then somehow the slope changes. Yeah, or it's why then it is not perfectly linear. Or you may force to linearize the whole thing, yeah, using linear approximation. You will have, for example, like this. Yeah, if you are doing the linear regression in Excel, yeah, usually you will obtain y equal mx plus b. Yeah, then you have the r square. The r square here shows the linear coefficient, right? The closer r square to 1, it means the more linear your line is. Yeah, okay. So when your r square is far from 1, let's say 0, 0.0, let's say 0, 0.7, 0, 0.6, then you know that actually the data, your data is not linear, not perfectly linear. Okay, so this is one of the characteristic error in sensor. Usually what to do when we have such sensor, yeah, we can have multiple region. So we can calibrate it using two lines like this, one line and the other one is another line. So when we operate the sensor in this region, we use the first line. And when we operate in the second region, here from here to here, then we use this second calibration line. This is one way if we want to assume linear value of the measurement. But if we want to uh, be close to the actual characteristic of the sensor, then we can have also nonlinear calibration curve. Yeah, the equation that express that calibration curve is not linear equation anymore, but instead maybe you could use quadratic. You could use also natural logarithmic, or you can use other transcendental equation. Usually, this is uh, true, especially when you are using when you use biosensor, when you are developing biosensor. When you biosensors, because you use biomolecules, you immobilize biomolecules like enzyme, antibody on top of a substrate, and they will have a specific law of kinetics. And the calibration curve also will be governed by this law. Yeah, usually at the low concentration of the analyte, then the slope of the calibration will be very high. Yeah. Then after which it will start to saturate. It will start to saturate. The slope will change to will decrease slowly, yeah, until it flattens, until it is saturated. So this is because of the kinetics of the enzyme and substrate binding. Okay, then we have dynamic errors. Dynamic errors are errors in the sensor measurement related to the dynamic time, to the how the sensor can follow dynamic signal. The dynamic signals are signals that change with time uh, quite uh, fast. Yeah, for example, when you have instead of static signal, but you have, for example, oscillating signal with a frequency of 1 hertz, 2 hertz, 10 hertz, etc. So how can your sensor follow these changes quickly? If your sensor is slow, then it may not be able to follow the quick change of the biosignal. Okay, so so then we know what we call as response time, the amplitude distortion, and the phase distortion. Response time, for example, so when you calibrate but not calibrate against multiple values of standard, but rather with a single standard and try to follow the changes of the reading of the sensor with time. So for example, this is the changes of the reading y, and we know if, for example, the value that we put is a step, let's say it is a step This is the input value, X input. Okay, the value of the sensor will try to follow here. So this is a step value we put to the sensor starting from t equals to 0. Yeah, from t larger than equals to 0. So the sensor reading will try to follow this. Okay, so for example like this until it reaches some steady state value, yeah, of y output. So the value to reach 63.82%. Yeah? Remember the first order. If it is first order, 63.82%. Yeah, the value of 1 over xe, yeah, is defined as the response time. Then if the system of the sensor is second order, then you could have under them in which that you will have this kind of response. You could have critically damped response. Remember your electrical engineering too. You could have also over damped. Sorry, over damped will be more like this. Yeah, like this. Over damped, immediately damped, like that. Yeah, over damped, critically damped, and under damped. Okay. Errors can also be caused by environmental errors, yeah, which is derived from the environment in which the sensor is being used, like due to the temperature, vibration, altitude, chemical exposure, etc. So usually when you use a sensor, when you purchase a sensor and try to use the sensor in particular application, the vendor, the manufacturer of the sensor will provide you with the environmental condition at which you can operate your sensor. Yeah, for example, the operating temperature range from -50 to 50 degree, for example. Okay, now let's learn some sensor terminology. Sensitivity. Here in this particular slide, it is defined as the smallest variation of a variable or parameter that can be accurately measured. So actually, this is more of, I have to revise this. Yeah, this is more of the definition of resolution or limit of detection that we had discussed yesterday. Sensitivity actually, when you had your calibration, this is the input and this is the y is the reading. Yeah, you have the calibration chart like this. Sensitivity here is usually defined as, and this is the gradient, is the gradient of the slope. Yeah, delta y divided by delta x. So this is the sensitivity. So if you have approach or you have did calibration, linear regression to your calibration data and express the calibration as y equal mx plus b, for example, then sensitivity is usually this m part of this equation, yeah, the gradient. So you could say that if you say it by word, the sensitivity will be the changes of the output, yeah, the changes of the reading of the output of the sensor for every detectable, although it is related with LOD, yeah, with resolution, if for every detectable variation of variable of parameter that can be accurately measured. So it is related, yeah, with LOD, but what the definition here is not completely what sensitivity is. Yeah, for example, sensitivity of blood pressure transducer, yeah, this is correct. It is usually expressed like this in terms of microvolt is the unit of the output, while volt millimeter mercury is the unit of the input data. So it means for every change, there will be 10-volt output change for each volt of excitation potential. For every change in the input, how much the output will change. Yeah, so this is actually the correct definition of sensitivity. Yeah, the change in the output reading per this for every smallest variation of the variable that can be accurately measured. Yeah. If it is only like this is usually the definition of resolution. Or in chemical sensor or biosensor, we call it as limit of detection, LOD, as we have discussed yesterday. Okay. Sensitivity drift. Sensitivity drift is the slope of calibration curve changes due to an interfering input. So for example, when you do the calibration at the factory or at the lab, you have the input here and you have the output. The sensor slope is here. Then at the field, when you do another calibration, for example, due to the environment, due to some here or there errors, the slope changes. The slope is not, for example, this one is y equal to myx. The slope changes to like this, for example. So this is y equals to m2x. The m2 is not the same with m1. This is drift. Okay, this is drift. The slope of the calibration curve changes due to an interfering input. So for example, in the continuing from the previous example, the actual sensitivity of blood pressure transducer is not 10. However, it is 7.8 microvolt per millimeter mercury, for example. Okay. The range. The range is the usable reading from the smallest expected value of the variable or parameter being measured to the largest. Okay. So, for example, again, we do calibration chart. This is X, this is Y. Previously, for example, we did calibration and it looks like this, the calibration. So it is only linear at this region, while this one is already not linear anymore. So you could define, for example, the linear range of the sensor to be from 0 until this region. Let's say until X1. This is the range. So if you want a linear reading, then you range you read this the usable reading at least linearly from the smallest expected value. In this case, it will be 0 until the largest here is X1. If, however, you choose to use the nonlinear calibration, you may then extend the range not only until X1, but maybe until, let's say here, X2. Okay, so this is range. The usable reading from the smallest expected value of the variable or parameter being measured to the largest. Precision is the degree of reproducibility of measurement. Yeah, so remember the previous week note, yeah, precision, we have dealt precision and accuracy, what are the difference? Now, this is correct. Resolution is the smallest detectable incremental change of input parameter that can be detected in the output signal. So remember, yesterday, usually when we do have calibration from previous, this is obtained from several input standard. Yeah, the more the standard we use to do calibration, the better we will get the calibration chart. And remember to also measure during the calibration the background condition. That is when you don't put any stimuli to the sensor. Remember, if you have like this, then this is the 3 sigma of or the standard deviation, 3 times standard deviation at measurement at 0 condition. Yeah, then the LOD can be calculated from this 3 sigma. You put into the as the y. The 3 sigma becomes the y. So you put here into this y. So this value from the 3 sigma, this value, the x equal to mx. Yeah, for example, this value x here shows the resolution, the smallest detectable incremental change of input parameter that can be detected in the output signal, which we are sure it is not due to any random errors, any random interferences from due to the background errors. Okay. Accuracy is the maximum difference we have discussed accuracy yesterday between the actual value and the indicated value of the sensor output. So the actual value can be obtained using standard or using validation measurement. Okay. Okay, yeah. Offsets are output that exists when it should be 0. So yeah, as I mentioned in the previous slide, so whenever, for example, we obtain uh, when we have 0 input, the x is input is 0. However, the output already shows some reading. For example, in this region, so here this becomes the offset. Linearity is the degree to which output variation of an instrument follow input variations. Is referred to as the linearity of the device. So if you have the calibration and you do linear regression, so you express the calibration line as what? As linear line. Usually, if you do linear regression, you will also have this coefficient r squared. Yeah. So the closer r squared to 1, it means the more linear your calibration is. Okay. Then hysteresis is the measurement of changes of the input parameter, regardless of in which direction of the change is made. So when you sweep the input value from lowest to larger input value, and then it gives certain output or certain reading of the sensor of the instrument, then you return back, you decrease again that value of the measurement from larger value to the minimum to the smaller value. It will have another measurement. The two measurements from the previous one, increasing sweeping and then decreasing sweep, should ideally be the same, in which case then we don't have any hysteresis. But in reality, we usually always have hysteresis. Yeah, so that when there is a difference in that value of reading when you sweep the input from uh, lower range, lower quantity to larger quantity, and then when you decrease. Okay, this is the hysteresis due to the characteristics sometimes, many times due to the characteristics of the material used in the sensor, because it is uh, dissipating the energy, yeah, of from the input. Later there is a graph illustration, yeah, illustrating the concept of hysteresis. Response time, we have discussed in the previous slide, the time required for a sensor output to change from its previous state to final settled value within a tolerance band of the corrected value. So you can define yourself, what is your tolerance band? Is it 30%, 25%, 10%, 5%? Yeah, so that then you define your own response time. Okay, so this is the illustration of some of the sensor terminology. Yeah, so for example, here we have this ideal curve, right? The sensitivity here will be defined as the slope of this ideal curve, delta y divided by delta x, or if we speak about small gradient, yeah, dy divided by dx. When the slope changes due to the environment or due to the time, the aging, etc., sensitivity may change, becomes like this. The slope changes. So this is what we call as drift. Yeah, the changes of the sensitivity, the slope of the calibration. So this is drift. The dynamic range or the total range is this one from y max, from the y minimum until y max, the reading. But the range of the measure run could also be expressed from the x range, yeah, x minus or to until x maximum. Then here we have the hysteresis phenomena. So at the beginning, when you sweep the input, in this case, for example, in this case, it will be magnetic strength versus magnetic field. This was the red one. But when you decrease the H, it doesn't follow the same path, the red one. Rather, it follows this green path. And then to the negative value, following this blue path. And then when you sweep in again from from small value to the larger value, then you have follow this green path. Okay. So that is the what we call as hysteresis, the difference. Okay, so since time is up, so I will stop the